Today, I'm going to explain about the cumulative distribution function, and this is the example 4-4 about the hole diameter. For the drilling operation in the previous example 4-2, large x and small x consist of two expressions. In the previous example 4-2, the probability density function was (20) multiplied by the exponential minus 20 multiplied by x minus 12.5, right? When x is larger than or equal to 12.5. So in this case, we have to find out the cumulative distribution function. So the cumulative distribution function can be divided by two parts. First one is 0 when x was smaller than 12.5, right? And the other one can be obtained by the integration from 12.5 to x and 20 exponential minus 20 x minus 12.5 when x is larger than or equal to 12.5, right? Okay? So if we solve this integration, there will be minus exponential minus 20 x minus 12.5 from 12.5 to x. Okay? And this can be minus e minus 20x minus 12.5 minus e. If we substitute x to 12.5, this goes to 0, right? So this will be minus e to 0th power, okay? So what is this? Yeah, that is equal to 1. So this can be 1 minus e minus 20 x minus 12.5. Okay? So finally, this can be changed to 1 minus e minus 20 x minus 12.5. Okay? So this is the cumulative distribution function for the example 4-2. Okay? So I'm going to draw the description, the figure for this cumulative distribution function. This is the continuous random variable x, and y-axis indicate the cumulative distribution function, okay? And this is the 0, and this is the 12.5, okay? So in this case, when the x is smaller than 12.5, cumulative distribution function is equal to 0. And this is the one. When the x is larger than 12.5, we have the 1 minus e minus 20 multiplied by x minus 12.5 equation here. And as you can see, x goes to infinite, this goes to 0, right? So finally, when x increases infinitely, this curve is closer to the 1, okay? So this is the schematic description of this cumulative distribution function. Okay? And I'm going to explain about the probability density function and the cumulative distribution function. The probability density function, which is called PDF, can be determined from the cumulative distribution function, which is called CDF, by differentiating, right? Because we normally obtain the cumulative distribution function by the integration of the probability density function, right? So if we want to calculate the probability density function, we can obtain this value by differentiating the cumulative distribution function, okay? So the differentiation of the cumulative distribution function by x is equal to the probability density function, okay? And this is the example. The time until a chemical reaction is complete in milliseconds is approximated by the cumulative distribution function as shown in here, okay? The cumulative distribution function is equal to 0 when x is smaller than 0, and it is equal to 1 minus e minus 0.01x when x is larger than or equal to 0. In this case, what is the probability density function? The cumulative distribution function 0 and 1 minus exponential minus 0.01x when x is smaller than 0 and x is larger than or equal to 0. So in this case, to obtain the probability density function, we have to differentiate the cumulative distribution function by x, right? So dfx over dx should be, this is just 0, right? And what about this? This can be 0 minus 0.01 multiplied by e minus 0.01x, right? So this can be 0.01 multiplied by exponential minus 0.01x. So this is probability density function here, okay? And what proportion of reactions is complete within 200 milliseconds? In this case, we have to find out the probability of x when x is smaller than or equal to 200, right? And this is just cumulative distribution function, right? So this can be written as large F 200. Okay? Okay? And 200 is larger than 0. So we can simply use this equation. So this can be 1 minus exponential minus 0.01 multiplied by 200. Okay? That equals to 1 minus e minus 2. Okay? And that is equal to 1 minus 0.135, so that is 0.865. So this is the proportion of reactions which is completed within 200 milliseconds. And I'm going to explain about what is mean and what is variance of the continuous random variable. Suppose that x is a continuous random variable with probability density function fx. The mean of x, which is denoted as mu or large A large X, is the mu is equal to the integration x multiplied by the probability density function from minus infinite to infinite. Okay? So for the case of discrete random variable, what was the mean? The mean was the summation x multiplied by fx, right? That was the mean for the discrete random variable case. And as you can see, what was the difference between the discrete and the continuous random variables? That was just substitute the summation to the integration. Okay? And what is the variance of x, which is denoted as large V large X or sigma square, also can be expressed by this equation. That is the integration x minus mu square multiplied by the probability density function from minus infinite to infinite. Or there can be the integration of x square multiplied by fx from minus infinite to infinite minus the mu square. And for the case of the discrete random variable, the mean was, the variance was the summation of x minus mu square fx, right? Or there was x square fx minus mu square. Okay? This is the case of the discrete random variable. And as you can see, the formulation is identical, but the only difference is that the summation is substituted by the integration. That's the only difference between the continuous random variable and the discrete random variable. So based on these two equations, we can simply calculate the mean and variance of the continuous random variable. And the standard deviation of x is the square root of sigma square. Okay? This is also identical to the case of the discrete random variable. So this is the example. For the current measurement of a Cooper wire, in the previous example 4-1, the probability density function fx is equal to 0.05 when x is between 0 to 20. And what are the mean and variance for this case? The mean can be calculated by the integration from 0 to 20, right? Multiplied by 20 of x multiplied by 0.05 dx, right? This is the probability density function, right? fx. And this can be 1 over 2 multiplied by 0.05 multiplied by x squared from 0 to 20. Okay? And this can be 1 over 2 multiplied by 0.05 multiplied by 20 squared minus 0. Okay? And this can be 1 over 2 multiplied by 0.05 multiplied by 400. So 2 can be eliminated by dividing 400 by 2, and 200 is left. So the final value will be 10. Okay? So that's the mean for the previous example 4-1. And what is the variance? Sigma square is equal to the summation, the integration of x square multiplied by 0.05 dx from 0 to 20 minus mu square, okay? We can use this equation, right? And this can be written as the integration of x square multiplied by 0.05 dx from 0 to 20 minus 10 square, right? Because mu was already calculated here, in here. So this can be 1/3 multiplied by 0.05 multiplied by x to third power from 0 to 20 minus 100. Okay? And this can be 1/3 multiplied by 0.05 multiplied by 220 to third power minus 0 and minus 100. Okay? And this is 133.33. Okay? Okay? So the final value will be 33.33. That is the variance for the previous example 4-1. So based on these equations, we can simply calculate the mean and variance for some special case. And I'm going to explain about the mean of a function of a continuous random variable. This means that if the continuous random variable is expressed by the function, we can calculate the mean by using this equation. If x is a continuous random variable with probability density function fx, the large E, h large X is equal to the integration of hx multiplied by fx from minus infinite to infinite. Okay? So if the continuous random variable is expressed as the function, we can use this equation. X should be substituted by the hx. I'm going to explain this based on this example. In the previous example, X is the current measured in milliampere, okay? And what is the mean of the pure current? In this case, Hx is expressed by the x square, okay? So based on the previous equation, the mean for this case can be calculated by the integration x square fx dx from 0 to 20, okay? And this can be the integration x square multiplied by 0.05 dx from 0 to 20. This will be 1/3 multiplied by 0.05 multiplied by x to third power from 0 to 20. Okay? And this can be 1/3 by 0.05 by 20 to third power minus 0. That is equal to 133.33. So when we have the square current here, the probability in this case, the mean for this case is 133.33. Okay? And this is another example for the hole diameter. In the previous example 4-2, the probability density function of drilling operation is 20 multiplied by exponential minus 20 multiplied by x minus 12.5 when x is larger than 12.5. So in this case, the probability density function is not constant, right? So for this case, what is the mean? The mean was x multiplied by fx dx from 12.5 to infinite, right? Because x is just larger than or equal to 12.5 in this case. And this will be the integration x multiplied by 20 exponential minus 20 x minus 12.5 dx from 12.5 to infinite. So to calculate this, we have to know about the famous relationship, that is integration u dv over dx is equal to u multiplied by v minus v dv over dx and dx. That should be u, okay? We have to use this, okay? So, what is u? U is x in this case, right? And what is dv over dx? That is 20 exponential minus 20 x minus 12.5. Okay? And what is the du dx? That is just 1, right? If you differentiate the u by x, that is just 1. And what is v? That is minus e minus 20 x minus 12.5, right? If you have an integration of this equation, you obtain this value, right? For example, if you differentiate this, you can obtain this value, right? So, based on these four relationships, we can change this equation to, first one is a u multiplied by v, right? So, u is here and v is here. So, x multiplied by minus e minus 20 x minus 12.5, right? From 12.5 to infinite, okay? Minus What is V? V is here, right? Minus exponential minus 20 x minus 12.5 multiplied by what is du over dx? That is just 1 dx. Okay? So we have to calculate these two cases, and I'm going to express this as A and this as B. So for the case of A, that is x multiplied by minus e minus 20 x minus 12.5 from 12.5 to infinite, right? Okay? So when the exponential has minus infinite, this value will go to 0, right? Right? So 0 minus, and what about 0? Because when we substitute to 12.5, that goes to 0. So exponential 0, it goes to 1, right? So this will be x is 12.5, right? Multiplied by minus 1. Okay? So this will be just 12.5. Okay? And I'm going to explain about the part B here. And this should be the minus integration from 12.5 to infinite minus exponential minus 20 x minus 12.5 dx, right? And this can be changed to plus, right? And for this case, this minus 20 exponential minus 20 x minus 12.5 from 12.5 to infinite, right? If you differentiate this equation, you can obtain this value, right? x 앞에 20 앞에 떨어 나오죠, 그죠? 그래서 마이너스 20을 여기다 마이너스 20 곱하면 마이너스 20이 없어지잖아요. 그래서 여기 얻어집니다, 그죠? So in this case, when we substitute the x to infinite, this goes to 0, right? So 0 minus, and when we substitute 12.5 to here, this goes to 1, right? Because exponential 0. So this will be minus 1 over 20, right? So this will be 1 over 20, and finally this can be 0.05. So finally the mu is equal to 12.5 plus 0.05, right? That equals to 12.55. So that's the mean for this case, okay? And now I'm going to explain about the continuous uniform distribution. a probability density function of a continuous random variable x is expressed by this equation when this is the continuous uniform distribution. So when we think about the discrete random variable, we already know about what is uniform distribution, right? That means regardless of the x value, the probability density function or probability mass function is identical. Okay? That is the definition of the uniform distribution. So in the case of the continuous uniform distribution, we can have this graph. This is the probability density function, and this is the continuous random variable. And in this case, the x is between a to b. For example, this is the a, and this is the b. The x between a to b has the probability density function 1 over b minus a. Okay? Okay? So this is the schematic description of the continuous uniform distribution. And the probability density function can be expressed by 1 over b minus a. And what is the mean and variance of the continuous uniform random variable? The mean of continuous uniform random variable is expressed by this equation. Large E, large X is equal to the integration of x over b minus a dx from a to b. Why? Because this is the probability density function, right? So mu should be integration x multiplied by fx ds for the case of the continuous random variable. And this will be x multiplied by 1 over b minus a dx from a to b, right? So this can be 1 over 2 multiplied by b minus a multiplied by x squared from a to b, right? And this will be 2 multiplied by b minus a, b squared minus a squared over 2 b minus a, right? So this will be 2 b minus a, b squared minus a squared. Okay? And what is this? This is b minus a multiplied by b plus a over 2 b minus a. So this can be eliminated, right? So finally we obtain b plus a over 2. So the mean of the continuous uniform random variable is a plus b over 2 when x is between a and b. And what about the variance? The variance can be expressed by this equation. Why? According to the previous slide, the variance of continuous random variable was the integration x minus mu squared fx dx, right? And this can be rewritten as the integration x minus, what is the mu in this case? That is a plus b over 2. So a plus b over 2 square, right? Over b minus a. Because 1 over b minus a is the probability density function in this case, right? So dx from a to b. Okay? So I'm going to solve this equation, how we can obtain the b minus a squared over 12. This can be 1 over b minus a integration from a to b x squared minus a plus b x plus a plus b squared over 4 dx. Right? And this can be 1 over b minus a multiplied by 1 over 3 x to third power minus a plus b over 2 x squared plus a plus b squared over 4 x from a to b. Okay? And this will be 1 over b minus a multiplied by b to third power over 3 minus a plus b squared over 2 plus a plus b squared b over 4 minus 8 third power over 3 plus a plus b a squared 2 minus a plus b squared a over 4. Okay? And this can be rewritten as 1 over b minus a right? That is 4 by b to third power minus 6 a b squared minus 6 b to third power, right? Plus 3 a squared b plus 6 a b squared plus 3 b to third power minus 4 a to third power plus 6 a to third power plus 6a square b minus 3a to third power minus 6a square b minus 3a b square. Okay? We have this expression. And first, I'm going to consider the b to third power. Okay? We have total 3. b to third power here, here, and here. Right? So, if you have 3 terms, first we can obtain the b to third power, right? Right? 4 minus 6 plus 3, that is 1. And what about this case? A multiplied by b squared, we have this, and this, right? So this can be eliminated each other. So minus 3ab squared is left. And what about a squared multiplied by b? This, and this. Right? So that is 3a squared b is left. Why? This can be eliminated each other. And finally, what about the a to third power? Here, here, here. So finally we obtain minus a to third power. Okay? So what is this? b minus a to third power. Okay? So this can be eliminated and 2 is left here. So finally we obtain b minus a squared over 12. Okay? So based on this derivation, we can have the variance of the continuous uniform random variable as b minus a squared over 12. So we can simply use this and these equations to solve the mean and variance of the continuous uniform random variable. And this is the example. Let the continuous random variable x denote the current measured in a thin copper wire in milliamperes, and assume that the probability of x is fx is equal to 0.05 when x is between 0 to 20. And what is the probability that the current measured is between 5 and 10 milliamperes? So in this case, we have to calculate the probability of x when x is between 5 to 10, right? So this will be the integration from 5 to 10, 0.05 dx. That is equal to 0.05 x from 5 to 10. That should be 0.5 minus 0.25. Okay? So the answer will be 0.25. Okay? That is the probability for this case. And what is the mean and variance of this continuous random variable? This is the continuous uniform random variable, right? Because the probability density function is identical, 0.05. So, what is the mu? What is the A? A is 0 here, right? What is B? B is here. So, the mu is 0 plus 20 over 2. That equals to 10. What is the variance? Variance was b minus a square over 12. That is 20 minus 0 square over 12. Okay? That is equal to 400 over 12. That equals to 33.33. So, do you remember the example 4-6? There was the calculation of the mean and variance for the same case, okay, in the previous slide. And we obtained the same mean and variance, even though we used the different equations. So, for the case of the continuous uniform random variable, we can simply use these two equations to calculate the mean and variance. Okay? 그러니까 continuous random variable 아까 했을 때 이렇게 해서 mean 구하고 이렇게 해서 variance 구했잖아요. 그죠? 이거 구한 값하고 이거랑 똑같아요. 왜냐하면 이게 continuous uniform random variable 케이스니까. 그러니까 이렇게 접근할 필요 없이 요거 그냥 식 이용해서 푸시면 간단하게 나옵니다. 아시겠죠? fx가 상수일 때. And now I'm going to explain about the normal distribution, which is called 정규 분포 in Korean. The most widely used distribution of a random variable is the normal distribution, which is also referred as the Gaussian distribution. The location and the spread of the distribution are determined by mean, mu, and the variance. And these are the typical examples of the normal probability density functions with the different parameters mu and sigma square. And this is the probability density function, and this is the continuous random variable. And this case is that the mean is equal to 5. And as you can see, even though these two normal distribution function has the same, the mean value of 5, the shape is different according to the variance. Okay? So, variance normally indicates the scatterness of the data, which means that when we have a larger variance, the width is larger. Okay? And we have the smaller variance, we have the smaller width as well, which means that the older data point is close to the mean value. And as you can see, even though we have the identical variance here, 1, according to the mean value, the location is different. So, according to the mean and variance, we can have numbers of the normal distributions. Okay? The random variables with various means and variances can be modeled by the normal probability density function with appropriate choices of the center, which is the mean, and the width of the curve, which is the variance. And the normal probability density function is expressed by this equation. The fx is equal to 1 over root 2 pi sigma multiplied by exponential minus x minus mu square over 2 sigma square, when x is between minus infinite to infinite. And as you can see, to obtain the probability and the cumulative probability function, we have to integrate this probability density function, right? But as you can see here, the equation is so complicated. So we normally provide a table. As I uploaded in the portal. Did you download this one as well? Right? So we can use this table to calculate the cumulative distribution function instead of calculating this equation. Okay? But we have to provide the standardizing method because, as I explained in the previous slide, we can have numbers of different normal distributions according to the value of mean and the value of variance, right? So by standardizing, we can have only one, the table, right? Which is called the standard normal distribution, which will be discussed in the later slide. So it is very important to have the standardizing method. 그러니까 normal distribution이 무한정 있잖아요. 뮤랑 베리언스에 따라서 무한정 있어요. 그거를 다 표를 줄 수가 없어요. 그죠? 이걸 다 계산하기 너무 복잡하고. 그러니까 이거를 표준 정구 분포 하나만 가지고 표를 준 다음에 다른 무한정 많은 normal distribution들을 스탠더다이징 시키면 그걸로 이동시켜주면 표 하나 갖고 다 계산할 수가 있겠죠. 그게 스탠더다이징입니다. 뒤에서 나오는. So this is the definition of the normal probability density function, and the mean is referred as mu, and the variance is referred as sigma square here. And the notation large N, mu, and sigma square is used to denote the normal distribution. And this is the example for the application of normal distribution. And assume that the current measurement in a strip of wire follows a normal distribution with a mean of 10 milliampere and a variance of 4 milliampere square. Let X denote the current. And what is the probability that a measurement exceeds the 30 milliampere? In this case, we have to calculate the probability of X when X is larger than 13, right? And the current measurement follows a normal distribution, which means that to calculate this, we have to provide the integration, right? From 13 to infinite, right? And fx dx, right? And in this case, what is the fx? That is 1 over 2 pi sigma exponential minus x minus mu square over 2 sigma square dx. It is very complicated to calculate this equation, right? Right? So as I mentioned in previous slide, we normally use this table by applying the standardizing method. And this equation shows this curve. And this is the probability density function. And this is the continuous random variable. And this is the normal distribution curve. And in this case, the mean was 10, right? And we have to calculate the probability that a measurement exceeds 30 milliamperes. So this is the 30 milliampere. So in this case, we have to calculate this shaded area. Okay? So for this question, we can just simply express this figure and this equation. 이거 그냥 적분이 안 돼요. 그래서 풀기가 굉장히 어렵다는 거예요. 그래서 수치적으로 굉장히 복잡한 식을 써서 풀든지, 뭐 프리의 급수나 이런 것을 이용해서 풀든지, 아니면 이게 스탠더드 라인 시켜가지고 이 테이블 이용해서 풀든지 이렇게 선택하시면 됩니다. So this is the empirical rule for normal distribution. And regardless of the mean and variance, we can have this relationship. Okay? 그러니까 mean하고 variance가 상관없이 이거는 경험적으로 이렇게 갖는다고 증명이 돼 있어요. So when the probability of x is between mean minus standard deviation and mean plus standard deviation is approximately 68%. Okay? This shaded area. And the probability of x when x is between minus sigma, mu plus 2 sigma is approximately 95%. And the probability of x when x is between mu minus 3 multiplied by sigma and mu plus 3 multiplied by sigma is approximately 99.7%. So regardless of the value of mean and variance, all normal distribution follows this relationship. Okay? And now I'm going to explain about the standard normal distribution. A normal random variable with the mean is equal to 0 and the variance is equal to 1. This is called the standard normal random variable. And it is denoted as large z. The cumulative distribution function of a standard normal random variable is denoted as the pi z, which is equal to the probability of z when z is smaller than or equal to small z. Okay? And appendix table that I gave to you provide the cumulative probabilities for the standard normal random variable. Okay? So this is the example for the standard normal distribution. Assume that z is a standard normal random variable and find the probability of z when z is smaller than or equal to 1.5. And this is the graph. And as you can see, mu is 0 here. And the variance is 1, okay? So in this case, we have to find out the area of this shaded area, okay? Right? Because the probability of z when z is smaller than or equal to 1.5 here. So this is the table that I gave to you. And this column is the indicator small z. And in this case, 1.5 is the small z, right? Right? So the probability of z when z is smaller than 1.5 is 0.933193. That is the answer. Okay? 이게 지금 cumulative distribution function이죠. 그죠? 마이너스 무한대부터 1.5까지 이쪽을 곱하는 거예요. 그죠? 더하라는 거예요. 계산하는 거예요. 이 테이블이 그냥 cumulative distribution function을 나타낸 거예요. 스몰 z에 따라서. 이해돼요? 그러니까 이 표를 이용해서 여기가 스몰 z니까 이 스몰 z가 1.5인 구간 이 값이 그냥 cumulative distribution function에 대한 해라고 보시면 돼요. 아시겠죠? So what is the probability of z when z is smaller than or equal to 1.53? And this indicates the z, small z, right? And this indicates the last value, okay? So 1.53 should be this point, okay? Because this is 1.5 and this is the point 0.03. So this is the 1.53, okay? So this value will be this one, 0.36992, okay? And what is the probability of z when z is smaller than 0.02? That is just here, right? Okay? So by using this table, we can simply calculate the cumulative distribution function. Okay, and I'm going to give you this table when we have the first midterm exam. Okay, so you don't have to worry about the table. Okay, and this is another example. And what is the probability of z when z is larger than 1.26? So the probability of z when z is larger than 1.26. And this is not the cumulative distribution function, right? Right? If we want to have the cumulative distribution function for this equation, we have changed this equation to 1 minus probability of z when z is smaller than or equal to 1.26, right? Because this is the cumulative distribution function. 그죠? So this will be 1 minus what is the probability of z when z is smaller than or equal to 1.26? Based on this table, there is 0.896165. Okay? So the answer will be 0.103835. Okay? And what is the probability of z when z is larger than minus 37? This equation indicates this shaded area, right? Right? And since this is the standard normal distribution case, which means that we have to, the center point, mu is equal to 0 here, and the variance is equal to 1, right? So this will be identical to the case this shaded area, right? Right? Because the center point is 0 here, right? And this part is identical. So the probability of z when z is larger than minus 1.737 should be equal to the probability of z when z is smaller than or equal to 1.37, right? So you can use this table again, and the answer will be 0.914657. Okay? And based on this concept, this also can be calculated by this equation. Right? Right? 1.26보다 크다는 거는 반대로 마이너스 1.26보다 작다는 거랑 똑같죠. 그죠? 작다라고 들어가면 저희 cumulative distribution 펑션을 쓸 수 있잖아요. 그죠? And What is the probability of z when z is between these two values? The probability of z is between 0.37 and minus 1.25, right? And this is this shaded area, right? Right? So this can be the probability of z when z is smaller than 0.37 minus probability of z when z is smaller than minus 1.25. Okay? So just we can use this table. The answer will be this is the answer, okay? And this is the end of today's class. And I'm going to explain about the standardizing in the next class. And I'm going to solve some problems of your first assignment and second assignment, okay? So the scope of the midterm exam is from chapter 1 to the normal distribution in chapter 4, okay?